Hello and welcome to chapter 23. We're going to talk about broad patterns of evolution. You must know methods used to date fossils and rocks and how fossil evidence contributes, that should say 2 hour, right there, 2 hour understanding of changes in life on Earth. So when we look at fossil history, we need to remember a few things. We need to remember that the fossil history is very much skewed. It's very much skewed toward organisms that had hard bones or bony parts or hard shells. Is also skewed toward organisms that lived a very long time and skewed toward organisms that were widespread around the planet. And so when we look at this, we look at the examples of fossils that we found, we have to bear in mind that the fossil record is an awesome resource, but it's also incomplete. And so don't worry about spending time trying to remember, this weird thing lived here and this weird thing lived here and whatnot. But what I want you to understand is that what we get out of a fossil record is an incomplete record. So what do we actually do with fossils? Well, we can try to date them by doing carbon dating if they were recent enough, or we can do dating of other chemicals in the rocks that are around them. But regardless, we use some kind of radiometric dating to try to find an actual number for years ago that this thing lived. And what we do is that we look at radioactive isotopes. And again, if we're looking at the skeleton itself, if it's recent enough, then we might look at carbon-14, we might look at uranium if we're looking at rocks from a very, very, very long time ago. And essentially what happens is that as things grow, they incorporate carbon into their bodies. And so that is, as long as you're alive, you have the same amount of carbon, of radioactive carbon, carbon-14 rather, in your body as is in the atmosphere. Well, once you die, you stop incorporating carbon into your bodies. And so then those radioactive isotopes decay. And so what we do is we say, okay, we know that decay is happening at a predictable rate. And if decay is happening at a predictable rate, when we find exactly half of the original amount of isotope, we do comparisons, we know that that is 1 half-life. And we have figured out the half-lives for a variety of different radioactive isotopes, and you don't need to memorize any of them. College Board would tell you. But what happens is that scientists just look at the ratio between the parent and the daughter isotope and figure out how many half-lives that is, and from there, then they can actually calculate the age of a fossil, either based on the fossil itself or on the age of the rocks that are surrounding the fossil that were presumably put there at the same time frame. All right, you have to know how continental drift can explain the current distribution of a species. This is called biogeography. And so, biogeography, the scientific study of the geographic distribution of a species. And those distributions of species can be influenced by a lot of factors, such as how motile they are, how much they move, those kinds of things. But one of the factors we're going to talk about here with biogeography is continental drift. And so we can use our understanding of evolution as well as continental drift to predict where fossils might be found. And so this is Pangaea, and this is just showing you how the continents move over time. And we talked very briefly in class about how the continents move with relation to them being on tectonic plates and floating on the mantle and convection currents and that kind of thing. You don't need to know a lot about that except to know that very, very, very slowly our continents are moving. And they're moving at a rate of most of them centimeters a year. And so what's happening is we can see, so here's the subcontinent of India, there's Madagascar, and here's Africa. We can see that over millions of years, this subcontinent smashed up into Asia. But by looking at the species of frogs, we can see that the species here and the species here are very, very, very closely related. So that's an example of biogeography, of using our understanding of evolution as well as the movement of the continents to predict where we would find very similarly related species. You have to know how extinction events open up habitats that may result in adaptive radiation. Okay, you don't have to actually know the names of any of the mass extinctions. They all have names, and that's fine. But this is a graph I showed you in class, and this is showing you these spikes are indicating extinction rates. And so this is a mass extinction, this is a mass extinction, this is one, this is one. People are predicting that we're having one right now as well, but obviously we don't know that till after the fact. And so, you know, we'll see. Well, you and I probably won't see, but someday we'll know if we're in a mass extinction right now. The blue line, in contrast, is the number of families. And so what's so very, very interesting about this diagram is how the number of species, the extinction rate goes up so fast. But notice that here, we're not actually losing a ton of families. And then it rapidly recovers. And same thing happens here. We have this extinction rate goes really high up, our families go down, but then once our extinction rate goes back down, now we actually see an increase in the number of families. And actually we're seeing an overall net increase in the number of families, even though in this same period we've had 2 mass extinctions. So what's actually happening is that when these mass extinctions occur, they wipe out huge numbers of organisms, but what they leave behind are unexploited resources. And those unexploited resources then become opportunities for speciation events for the remaining organisms. And so that's what this graph is showing you, is that even though we have like a couple of major extinctions here and here, the diversity is actually increasing because that's opening up niches for organisms that are still alive to then go through speciation events and take advantage of. And that is actually what this is indicating to you here. And so it's looking specifically at predators, but I want you to just notice the trends here. And so when we have a mass extinction, does not mean that everybody's dying out, but what it does mean is that more niches are becoming available to these as a result of so many organisms being wiped out. So then what does that actually mean as far as phylogenetic trees are concerned? Well, if we have a mass extinction, it's represented like this, with this kind of, I don't know, horn-shaped tree. What this is saying is that, you know, if we have adaptive radiation, we have you know, all of the reptiles, the dinosaurs all died out, all of those organisms are no longer with us, they're extinct. That has opened up a lot of opportunity for eutherians to be diverse and marsupials to be diverse. The opportunity exists for monotremes as well, but they didn't undergo the speciation events. And so once we have a mass extinction, it just gives opportunity, an opportunity for speciation events. Doesn't mean it's going to happen, but it means that that opportunity does exist. So that's it. That's the end of Unit 6. Thanks for watching all my videos. I hope you guys have a good day, and I'll see you in class.